This video is brought to you by Hackeramo Chalk. Use code TPSA 10% off to get a discount.
Welcome to this lecture on the foundational aspects of quantum computing. My name is Connor, and I'm a PhD student in Trinity College Dublin and also part of the IBM Qiskit Advocate program. I will be giving this lecture to begin a series of lectures from TPSA's involvement in the IBM Qiskit Fallfest 2025. So the structure of this introductory lecture will be to just introduce ideas from quantum computing and why they might be useful or different from what is known as classical computing, and then to move forward into more future ideas that look at challenges and possibilities, just to introduce a collective idea of what is currently there, how it functions, and where it could go. So for the introduction, there's no point introducing quantum computing without first introducing quantum mechanics. Quantum mechanics is the part of physics which fundamentally underpins the entire workings of quantum computers, and where it comes from is the laws of physics that basically dictate the behavior of matter and energy on the smallest scales, ranging from molecules to atoms to subatomic particles and as far down as we can get. So where this comes into quantum computing is that these laws of atoms and these very small objects are utilized to perform computations. So if you have a qubit, a quantum bit, the quantum analog of the classical bit, you can have it in the familiar classical states 0 and 1, but differently to classical computing, you can have superpositions, a quantum behavior that we'll touch on a bit more later, where you have a linear combination of 0 and 1, not just from statistical uncertainty, but something where they are fundamentally in a superposition. So what this does is this typically provides a range of different answers depending on quantum measurement outcomes that are probabilistic, as quantum mechanics, unlike classical physics, is probabilistic and not exactly deterministic in all aspects of its behavior. So for a classical computer, like the laptop or phone or desktop you would be watching this lecture on, they operate based on bits, where they are only 0, 1, and nothing else. Exactly that. And what you do is you perform a set series of operations on these bits to transform a collection of them to some desired outcome that should be deterministic and a singular answer in form. This is also done sequentially, ordering the operations A, B, C, if we ignore extra complexities such as parallel computing and things like that. So, before we continue with the behaviors of quantum computers and what they can do, it should be noted to keep in mind why exactly are we interested in this, other than the fact that it is different to classical computing. Well, when you do classical computing, not everything can be done to an exact level, and certain difficult calculations require a variety of approximations to be performed in a feasible timescale for classical computers, and with the current resources that are available, such as memory. But there are still a class of problems that, even with these well-designed approximations, still cannot be solved within reasonable timescales or using a realistic amount of resources. These problems, for example, could be simulating complex quantum behavior in nature, where you have a many-body quantum system, or you need a large-scale system that requires a better description at this small scale, such as proteins for drug discovery and chemical reactions, or a particular problem that can be mapped to one of a quantum mechanical nature and exhibit behavior that requires optimization or processing of large amounts of data. So we see here from the diagram that problems that are classically feasible are a small subset. Then there are problems that can be solved using quantum computers, which contains the classical problems. And then there's a set of hard problems that exist outside what can be solved classically, but can be solved using a quantum computer. Now, pay attention to the fact that not all hard problems are contained within the quantum solutions section of this Venn diagram. Just because a problem cannot be solved in a classical computer does not mean a quantum computer will solve it and all problems become tractable. There would still be potential problems which are hard either way. But the key thing is that there are problems which are difficult classically, which should be possible to do on a quantum computer. Now, this won't lead to, say, the overthrowing of classical devices like laptops and phones, where they will all be replaced with quantum mechanical upgrades of them. Something that is done classically will stay classical because that is done efficiently and simply, and we know how to do it well. And where there's no point to change to a quantum solution, it is unlikely that will happen. Where quantum computers will come in is that they will build on the existing classical capabilities that we have in our current technology and tackle the problems which are difficult. So we won't go looking for quantum ways of doing things that we already know how to do in a well-defined classical manner. So, now that we've established why it is interesting to use a quantum computer, we'll take a deeper look into how exactly they work. So, as explained before, we have a classical bit where it is 0 or 1, so like a light switch which is either on or off, or a coin where it is heads or tails. Two very well-defined states where they are always one or the other. Whereas for a quantum bit, we have these states 0 and 1 with a different looking notation than just the numerical values to indicate, for those of you more familiar with the structure of quantum mechanics, the physics and mathematical sense, that they are state vectors. And when we have two state vectors that form the basis of a vector space, for instance, the rest of the vector space will contain linear combinations of these basis vectors, and all we require for quantum mechanics is that they can combine in such a way that the laws of probability are conserved, and if we have a superposition where we have equal probability of measuring 0 and 1, that would be one such example of a valid superposition vector. So this is unlike what we see in classical physics, where if you have a coin, it is always heads or tails, even if at some particular instance of time you might not know which. That just boils down to classical ignorance, rather than any actual mixture of the coin being both heads and tails at once. Whereas quantum mechanically with a qubit, that is actually the case, and is going to be important when we scale up to many qubits. So, in a more mathematically defined sense, as mentioned before, you have 0 and 1 as your possibilities, and they can combine in a vector form as such with quantum amplitudes alpha and beta. So alpha and beta do not represent the probability of measuring 0 and 1 directly, but instead can be complex numbers whose absolute values squared would give the individual probabilities of measuring each quantum basis state, 0 or 1. Just like a classical bit, still 0, still 1 when you measure it. And then we have to obey the laws of probability, so the sums of these absolute value squareds must be 1, because no matter what we get in the measurement, it has to be something out of all possible measurement outcomes. Now, to do interesting things with a quantum computer, you would not require just one single qubit, but a large collection of them. So if we go and scale up to 2 qubits, for instance, we would have 4 possible classical outcomes: 0, 0, 1, 0, 0, 1, and 1, 1. So any quantum state vector we want to make would be a linear combination as shown here, with quantum amplitudes alpha 0 to alpha 3. So again, to obey the laws of probability, the absolute values squared of each of these amplitudes will sum to 1. And if we build a little table up to see one qubit can exhibit 2 states, 0 and 1, as a classical bit would. 2 qubit system will have 4 basis states of its vector space. Again, the 4 classical outcomes you would still have for any regular computer, and we keep going up. We'll be multiplying every successive vector space with all our possible quantum state vectors by 2. So for 3 qubits, we would go up to 8 basis states and all of their combinations. For 4 qubits, 16 basis states and all of their linear combinations. So the number of basis vectors we require to understand the vector space that our quantum vector would exist within will scale as 2 to the power n, where n is the number of qubits that we have. So this is in fact an exponential scaling. So if we go to the size of a quantum computer or a realistic quantum system that we would want to study in nature, n would in fact be quite large, even if something we say 100 qubits. This will very quickly become intractable solve exactly with a classical computer, because you will need to store all of the basis vectors of your state vector for your quantum wave function, and also all of the amplitudes, these complex numbers that describe the combination you will be looking at a particular moment of, say, time evolution. So this is why, when studying quantum physics through classical resources, we require a variety of insightful approximations and tricks to do it efficiently. But once n becomes very large, or the system exhibits particular features that cannot be approximated quite well, the problem still becomes intractable, and this is where quantum computers can step in and become more efficient for us. So now when we have a linear combination of our quantum state, reducing our system back to one qubit, we would have the one qubit possible state vector alpha 0 plus beta 1. And then we perform a measurement on this qubit and we obtain an outcome. When we perform the measurement, all we can obtain is classical information. You can measure in different bases, for example, the Pauli Z, X, or Y bases, or different clever multi-qubit bases to get 0 or 1 back, but all you can obtain is classical bits, which can be read out. So you obtain classical information back. So we have our superposition state, and to obtain exactly what state that might be, we would have to measure it a large number of times to build up a statistically significant amount of outcomes to determine the probabilities of measuring each state. So when we measure, the state vector will collapse into 0 or 1, the classical basis states which are not showing any quantum behavior such as superposition. And then, once we measure a few times, so in this diagram here, 1024 shots would be 1024 repetitions of some experiment and a measurement at the end. And then you can plot a histogram showing the number of 0 outcomes and the number of 1 outcomes, and dividing that by the total number of measurements, you will see the probability of measuring either 0 or 1. So in the top diagram, that would be 50% of each. In the bottom left one, you would have a probability of, say, 0 for 0 of 100%, and this can vary depending on what your state is. All that matters is that you, to a statistically allowable amount, conserve the laws of probability. Now, when we go to the more relevant case of multi-qubit systems, where we're looking at significant behavior of how to leverage the fact we have multiple qubits to gain a quantum advantage from, we're not going to look only at superposition, but also at the behavior of quantum entanglement. So quantum entanglement comes from when we have two qubits that are linked such that we cannot describe their states independently. In the more mathematical formalism, quantum mechanics, for those of you familiar with it, this means that if you have a quantum state vector, a pure state vector such as the Bell state shown here, of your multi-qubit system, and you try to factor it over your two entangled or potentially entangled subsystems using a tensor product of state vectors on each system, if the combined systems are entangled with each other, you cannot perform this factorization into a tensor product of pure states. But if you can perform this factorization, it means you just have a product state and there is no entanglement. So looking at this Bell state here, we can see that we cannot factor out a state of something on qubit 1, tensor product, another state on qubit 2. So when you perform a measurement, then on this entangled system, the outcome of the other qubit will be affected by the measurement on just one single qubit, meaning there is a correlation between them such that you don't have to measure all qubits at once to obtain full knowledge of the system. So that is, of course, the problem that was notorious with Albert Einstein, where he felt that violated relativity with an instantaneous transmission of information from one qubit to another, but in fact, verification that this information has been measured requires the transmission of classical information, which would preserve relativity in a sense. And entanglement will be shown to be one key component to leverage the benefits of quantum computers over their classical counterparts. Now, when you are performing operations on a quantum computer to transform the quantum state of your qubits to some desired outcome you want to measure as part of your quantum algorithm, you will be utilizing quantum interference. So quantum interference is when you have two or more quantum amplitudes, those alphas and betas that multiply your quantum basis states, and they interfere with each other, so add together and subtract for each individual basis vectors, and that will either lead to a larger quantum amplitude or a smaller quantum amplitude for each state vector, where in fact if you don't want to measure one, you can interfere in such a way that you reduce its amplitude to 0, or if you want to guarantee a particular outcome at the end of your algorithm, you can try to get the amplitudes to interfere in such a way that your resulting amplitude will be 1, for instance. So while we are discussing this as operations on vectors, this would come from the wave nature of quantum particles, very much as you are familiar with that type of interference, where you have two waves interfering with each other, either enhancing their amplitudes at certain points or cancelling out destructively to get rid of features you don't want in the outcome of your quantum computation. So this is useful for one of the fundamentally important or fault-tolerant quantum algorithms such as Grover's search algorithm, where you want to find a particular quantum state that is in your solution space, so you search through all the possible solutions and enhance the amplitude of the one you are looking for, and aim to measure that by also reducing the amplitudes of the states that are not in your solution space. Now, if you want to do this interference or any sort of calculation using qubits rather than classical bits, you of course need an instruction set for how to do that, just as you would on a classical computer with gates like the AND gate and the NOT gate. We need quantum mechanical analogues that can both perform these classically familiar operations, but also get us to leverage the quantum benefits such as superposition. So for example, we have this quantum circuit here with qubits Q0 and Q1, and we have our time axis here showing the order of our operations we perform on these two qubits. So the Hadamard gate, for example, is one of the most well-known quantum gates, which puts the qubit into an equal superposition. So a 50% chance of measuring 0 and a 50% chance of measuring 1. And that is a single qubit gate in that it does not act on qubit 1. Then we act with the C0 gate, a controlled NOT gate, which means we act with the NOT operation on qubit 1, controlled by the state of qubit 0, meaning depending on what qubit 0 is, we will either perform the NOT operation or we will not. And there are other gates, such as the Pauli X gate, which is exactly the classical NOT gate, but also the Pauli Y and Z gates, S, T, and P gates, which change the quantum phase of your state, and a variety of others that can be used or would form a basis set of gates where any desired gate can be made from a combination of the gates you can perform on your quantum device. Then at the end of the algorithm, past this barrier, we will perform a measurement on each qubit, as shown on qubits 0 and qubit 1, and measure onto a classical bit register, and then read the classical information out. So this is the quantum block sphere, which illustrates what a single qubit state might look like. So we have our 0 state and our 1 state, our basis vectors for the single qubit, and any arbitrary single qubit state vector psi would be a point on this sphere. So you would start with whatever state vector you desire, say a classical input such as 0, which is quite common for quantum algorithms, and any operation you perform on it, such as the Hadamards, the S gates, the X gates, Y gates, Z gates, will just be rotations around this block sphere, and you will get a new state vector psi, which can be parameterized by the spherical angles phi and theta. We would have the 0 vector, and if we perform the X gate, for instance, we would be doing a classical bit flip and flipping it to the 1 state. Or if we want to do something more quantum mechanical like we did before with the Hadamard gate, we would flip it to the x-axis of this sphere, where it is halfway between 0 and 1, representing that 50-50 probability of measuring either of our two classical outcomes. So, I've used the word qubit in each of these examples, which does not refer to any specific real-life physical quantum mechanical system. So what actually is this two-level system? Well, depending on what device you're using, it could be a variety of quantum mechanical objects. For instance, on the IBM quantum computers, they utilize superconducting qubits, as well as Google, where your superconducting states would be your 0 and your 1. Or there are other quantum computers that use neutral atoms, where two different atomic states will be selected, with one being 0 and the other being 1. Then you have nitrogen vacancies in diamond, where you might have an electron spin state, where spin up could be 1 and spin down would be 0. Similarly, for photons, you could encode your 0 and 1 in polarizations, trapped ions, and quantum dots behave analogously. So there are a plethora of qubit architectures you can choose for your device, with each bringing different benefits or problems to address, depending on what you want to do in terms of increasing your number of qubits or getting them to interact with each other in the way you want or perform particular operations. And that is why so many different quantum computing companies are exploring how to build quantum computers using each of these quantum mechanical platforms. Now, we've seen theoretically and mathematically some of the foundational concepts behind quantum computers and what quantum mechanical objects they might be made from. Well, what does a full quantum computer look like? Well, for one example, this is an IBM quantum computer System 1 from 2021, so quite old at this stage, and in this picture looks like part of the spaceship, but doesn't really highlight the inner workings of the quantum computer and what actually is required to do the operations, or where in fact the qubits even are in this image. So a better image, such as this one, presents a quantum computer more like a technological looking chandelier. So the entire quantum computer would be this system, but the quantum processor, where the quantum mechanical objects are, would be more at the base of this chandelier, or dilution fridge would be a part of it. So all the wires and extra pieces of equipment that are not part of the processor itself would be to do with sending and receiving signals from the qubits to perform the operations you want as part of your algorithm, and transmitting them to the classical servers, which connect to your laptop or desktop and gives you the results back from the quantum device after first receiving the operations you wish to perform. Within this, not contained in this image, would be the cooling equipment to make a quantum computer operate, because they typically have to be cooled to temperatures such as millikelvin to limit interactions with unwanted parts of the environment, which will be explained a bit more in a minute. A more recent look then at the IBM fully complete system would be like this, again where you cannot see too much of the quantum computer itself, but this would be the storage aspect of it completely from the outside. Zooming in now to see what exactly is the quantum part of the computer will be this. This is the quantum processor that is contained within the base of that chandelier looking object. So this would be the IBM Heron processor, which, as shown on top of it, contains 156 qubits. So this would be 156 superconducting qubits contained in some sort of structured array, where you have, say, interactions between neighboring qubits, but not through all-to-all connection. So each processor has to be constructed with a certain architecture and design to enable as many quantum operations in as simple a manner as possible. Now, I have explained a bit some of the fundamental ideas behind quantum computers and what they look like, and a little bit about what they can do. So the question then remains of, why are we not just designing quantum computers and solving these problems then? And the simple answer is that it is not quite that easy. There are several challenges that need to be addressed to effectively design a quantum computer at the scale and with the capability we require for the problems that are beyond our classical capabilities. One such issue is quantum noise. Now, this does not mean noise as in the sense of sound, although it does play an analogous role. If you want to detect some sound signal, but it is drowned out by surrounding noise that you do not want, you cannot detect the signal you want, and that is why we use the label noise in relation to this, because quantum effects that are undesirable influence the noise, the quantum outcome we want to obtain from our quantum computation. So there are a variety of noise sources, such as coherent noise. This could be caused by an imperfect quantum gate causing over or under rotations. So if you think back to the block sphere example we had, where your single qubit state exists somewhere on that sphere, if we wish to perform a quantum operation that rotates to a certain point, but it is imperfect and we rotate a bit past or to a bit before that point, we will have a slight error in the state we are expecting. And if you perform quite a long computation using this operation multiple times, the error will build up. Then we have incoherent noise. So where we have coherent noise, we know if we under or over rotate, we could detect this error and perform the operation to rotate the state where we need it to be. That is why it is coherent. No information is fundamentally lost. It is just an error in the performance of the operations we wish to do. Whereas in the case of incoherent noise, if you think of your qubit surrounded by a larger environment which is not part of the quantum system we are interested in, but the wider world around it, such as the electronics, the devices, the room the quantum computer is in, you can lose your quantum information to that surrounding environment, and that cannot be retrieved. You also have errors such as state preparation and measurement. So if you wish to prepare a quantum state, typically at the beginning of a computation would be the all-zero state. You can do that with a high accuracy, but it might not be a perfect accuracy. Similarly, for measurements, you would still have some measurement noise where you can get a perfect measurement with some probability p, but there will always be probability 1 minus p that instead of measuring 0, you might measure a 1 instead, and vice versa. You also have projection noise. So because a quantum computer is probabilistic, so it's not perfectly deterministic in every step of what it does, you can still get random fluctuations in your quantum measurement outcomes, but you can get a statistically high enough amount to overcome this in most cases. So this shows that in fact a quantum computer, while it can do a lot, there's still a lot we need to also be aware of in using them to the capabilities we wish to tackle the problems that we wish to solve. Now, we have quantum error mitigation as one potential way to overcome this. So quantum error mitigation takes the measured outcomes of our noisy quantum experiment, for instance, and post-processes the results to then get a higher accuracy. So there are several possible methods you can use to post-process your results, such as zero noise extrapolation, where you repeat the experiment multiple times, enhancing the amount of noise in it, obtaining results, and then plotting them to extrapolate back to the point where you have zero noise. You can also use twirled readout error extinction, probabilistic error cancellation, and a variety of complicated or sometimes simpler methods depending on how much error mitigation you wish to perform on the results. So this graph here shows a bit of an example where we have no mitigation on the expectation value of some quantum operator that we are interested in, and we see if we perform the experiment it sits around 0.9. Then in the ideal case, if there was no noise, we would want it to be around 1. So applying different error mitigation techniques, we notice that each can have a different effect. So depending on what the noise is, each method will have its own benefits in terms of what it can mitigate. They won't each work equally. Some will be better, some might not have such a large effect. As you can see here, dynamical decoupling and world readout error extinction don't really do a whole lot and in fact decrease the expectation value, whereas zero noise extrapolation brings you almost to the ideal case. Now, we've seen foundationally how a quantum computer works, what we want to do, and how we can tackle some of the challenges that we still face today. And this can let us characterize where exactly we are with the state of quantum computing. And one of the cases for quantum computers is the era of quantum utility. So this is where we begin looking at problems that might begin pushing beyond what is classically feasible. So quantum utility specifically refers to any quantum computation that provides reliable, accurate solutions to problems that are beyond the reach of brute force classical computing quantum machine simulators. So there are a couple of keywords to pick out here, such as brute force. So that would be your classical computer does it without any kind of clever tricks, methods, or approximations. So this does not mean the classical computer outright fails and the quantum computer has directly overtaken it, such as in the case of quantum advantage, but it means that the quantum computer can keep pace with a classical solution that, while difficult, might still be in reach. To show a quantum computer is targeting a problem that could be relevant, classically difficult, but we can still benchmark it against an accurate classical result to test that the quantum computer is achieving solutions with a high enough accuracy to tell we are doing what we want with it. So for example, IBM have looked at some quantum utility problems, such as the one shown here in Nature, and they demonstrate that it is possible for a quantum computer to outperform leading classical simulations by learning and mitigating errors in the system, so not by sheer computational capabilities, but also with this classical post-processing of results using the quantum Eagle processor, where it has 127 superconducting qubits that can generate a large entangled state and simulate the dynamics of spins in some material, and also accurately predict properties such as its magnetization. So a large-scale quantum physics problem that would be classically difficult. Whereas if we wanted to go further, we would go into quantum advantage. So this is where classical computer no longer keeps pace, but instead begins to fall behind. So you would be using a quantum computer to deliver a solution which is in fact more accurate, also more achievable in terms of resources and time than a classical computer would. So we are not quite in this era yet, but it is the area we are aiming to go with quantum computers and hope they can begin tackling the problems that are difficult for classical computers. In this era, we would be looking to leverage quantum error correction. So this is separate from quantum error mitigation, where error mitigation is done on a classical computer after performing your quantum experiment. Error correction is done while performing the quantum experiment, meaning it requires more quantum resources, more qubits, and more gates in your circuit. And this will allow the operation to catch errors before or while they happen, meaning you can more effectively get results from measuring. So we need better gate accuracies to do this and better ability to put more qubits together. So we are not quite there in terms of leveraging proper quantum error correction, but it is very much a topical and interesting area of research that will become very, very important to move to an era of fault-tolerant quantum computing. So now that we've seen challenges and where we could go, we look at the future. So we could have large-scale quantum processors and hardware where we are not just looking at hundreds of qubits, which is a large amount, a relatively large amount for today, but in fact thousands, tens of thousands, or more qubits that really are what needed for these large-scale problems, and also that combination with quantum error correction to fully get accurate, interesting, and efficient quantum results out of your quantum computer. Then we have other areas such as quantum-centric supercomputing, so we won't completely get rid of our classical resources, so it is worthwhile to investigate where in fact we can combine the quantum and classical to get the best of both worlds. we have quantum algorithms. So if we have a problem we want to solve on a quantum computer, it is all well and good having the resources we need on the quantum computer to do that, but we must design quantum algorithms which will not just be quantum analogues of classical algorithms, but will use fundamentally quantum behavior to solve the problem. So while we are developing the hardware, it is also important that we address the need to develop algorithms in parallel, so that when the hardware gets to the level it needs to be, we have algorithms we can apply on the quantum computer to get there. Then to implement these algorithms, we must use quantum softwares such as Qiskit, which will be the focus of the remaining lectures in this series, and put together code bases for users such as researchers and students to use quantum computing for solving a variety of scientific problems. So thank you for listening to this lecture, and I hope you enjoy the rest that are performed in this lecture series as part of TPSA's IBM Qiskit Fallfest.